हाँ
Pressure from beginning. Okay, so last time we were trying to refine the crystal structure of a material for which the formula was lithium, nickel 0.5, manganese 1.5, O4. And when you want to refine the crystal structure of a material, first you have to make a PCR file. And of course, you should have data file. Now, this compound crystallizes in the space group, which in the full Prof PCR file is written as P433 space 2. And the space group number for this file is 212. So first thing before you start the refinement is just to go to the International Table of Crystallography, or you can go to Bilbao Crystallographic Server as I show you here now. So if you go to Bilbao Crystallographic Server, what you have here is, like I go to this Bilbao Crystallographic Server now. And I type Vico and it is 212 and then I go in the standard setting. So now you see the Vico position for this space group 212. So there are a couple of sites where your atom can go, and 24E is general site in this space group. So if you count this position in the unit cell, then you find there are 24 positions where this atom, if it goes at 24E site, its positions are given here. There are other sites like 12D, 8C, 4B and 4A. So these are the sites on which your atom can go. Now then, how to decide this occupancy in your PCR file from this from this information of this Wyckoff position. So what we do is, we know, let us take this example of this compound. So here there are 5 kind of atoms. So these atoms are these atoms are lithium, we have nickel, we have manganese, and we have 2 kind of oxygen in the crystal structure of this material. And from this, the information which I have already available from the literature is that lithium goes to 8C site, nickel goes to 4A site, manganese goes to 12A site, oxygen 1 is 8C and oxygen 2 is 24E. Now with this information, how we decide this occupancy? So let's try to write down the occupancy. To find out this occupancy, what generally we do is, we try to divide this special position multiplicity by this multiplicity of this general site. So for the lithium, the occupancy becomes 8 divided by 24, means 1 by 3, which is 0.3333. For this nickel, this occupancy becomes 4 by 24, means 1 by 6, 0.16667. Similarly, for this 12 divided by 24, 0.5. For oxygen, it becomes oxygen 1, it becomes 8 by 24, means again 0.3333. And for this, the occupancy is 24 divided by 24, which is 1. So this is the information about occupancy. And let's see what we did last time in this PCR file. So now I go to the PCR file. So how we start this full prof program is, let me close it. So you click on this full prof suite, and then there are a couple of ways to work it. How I work is, I first select this working directory. So in this working directory, you select the PCR file where you are working. I selected this PCR file, then I can see this content of this PCR file by click on this run editor. Now, if I click on this run editor, I find this information. This information is in the text file. So many people have problem in understanding this various notations of this file. So I will briefly like to tell you what are these keywords. And if you are interested, I have a small script sheet which I can send it to you so that you can remember at least few important things, like few important keywords in this PCR file. There is another way to see this PCR file is that you go to this edit PCR, and now by default it opens this PCR file which I have selected in the starting. And I can view this PCR file by clicking from here. So now this is the PCR file which is same whether I see it from here or I see it from here. Now let us see the meaning of various code words in this PCR file. You can see this code word either from this edit PCR tab, where like the first line tells you that, the first line here is this comment, and all these things which start after this sign, they are comment. So means the program do not read this. It is taken as a comment. So this line is not read by this program, and all these things are read by the program. Now this job type tells that what kind of job this program has to do it, like neutron refinement, structure refinement, or basically refinement with the X-ray. This NPR tells you this type of this profile, this picture, and NPH is telling me the number of phase. So right now in this PCR, we have only this single phase which is called nuclear phase. When we go to this magnetic refinement, we make this number of phase 2, or suppose you have a sample where there are multiple phases, like in your crystal structure part itself, then here you can put that according number of phase, but then you have to add this phase part here before this line. So this similar line one has to add it up if you are putting more than one phase here. This NBA is number of background point. So what it is telling me that I have point by point 35 background points which are mentioned here. So these are the background point. You can count 1, 2, 3, 4 like this. So there are 35 rows on which these are the positions, means these are the 2 theta values, and these are the corresponding intensity of that background. NEX tells me about this excluded region. So here NEX1 means I have one excluded region. As you can see it here, this excluded region is given between 0 to 5. So this is the region which will not be considered during the refinement. Other thing is NSC, means which defines that what kind of, if you are providing user defined some scattering length or some form factor, then you have to choose this factor. NOR code words tells about the preferred orientation. So if NOR is 1, then there is some function which is used. I will tell this function in the next lecture. And when if I am using NOR1, then if I put preferred orientation 1, then there is no preferred orientation in the sample. Means while this uh, profile is calculated, it is assumed that there is no preferred orientation. Any other major thing is this auto. So you can run this full prof file either in the auto 0 mode or auto 1 mode. If you run this file in the auto 1 mode, then all these parameters where I put it, let's say if I put it 1, this will be automatically refined. But for the beginners, it is advisable that you start with auto 0 and then whatsoever parameter you want to refine, you tell this program and this program will refine as per the direction given by you. So you can refine this scale factor. So like if I put 11, 21, so this all the digits which are below this parameters and which are ending with 1, so these parameters will be refined. So in this case, like suppose if I want to refine only 2 parameters, then if I am in the auto 0 mode, then what should I do is I should put it number of refined parameter 2. But here sometime you get some error, and the most of time the reason is like if you are working in auto 0 mode and suppose you do not define any parameter like 21 and if you directly come to 31, and let's try to do this experiment now, then this program is supposed to give some error. So I am running in this auto 0 means manual mode, and I have not given any code word 21 for the refinement. And let us see what it does now. So I save this and let me check it again. This program has saved it as auto 0. So this is auto 0. Now I can run this by run full prof. So now you can see it. This gives the error, a warning that hole in the normal matrix. And it tells you also hole in the normal matrix missing element 2. It means you have not given any code for the refinement of this. So you have to put, because you are asking it to refine these 2 parameters. So first, for the first you have given the code 11, but nowhere in the PCR file you have put the code 21. So I should put the code 21. Now, one more important thing, when you are running this PCR file in the auto 0 mode, so it will not try to refine the other parameters like this parameters here it is ending by the 1. So this parameter it will not try to refine it because it will try to refine only the parameter which you have told the program. So like if I write 2, it will try to refine the parameter where I have 11 and 21. If I write 3, then it will try to refine these 3 parameters 11, 21 and 31. But on the, so let's try to run this. And you can see it has refined only 3 parameters. Now let's go in this other mode, which is auto 1 mode. And here I do not have to tell it that how much parameter it want to refine, only it will try to search where is the code 1 existing. So let's put it, let me put it the code 1 here. 1 or 21, whatsoever code which is ending with 1, if it finds, it will try to refine those parameters. So now suppose even if I say to refine it only 1 parameter, and let's make all these things to 0. But it will refine only the parameters where it finds this, there is a 1 ending digit. Otherwise, Like if you have 0, 0, 0, it will not try to refine those parameters. Sorry. So let me, now I have put auto 1 and let me see what it does. I am saying it to refine only one parameter. Let us see now. Now you can see by default in the automation mode, program has refined 5 parameters. So it has refined all those parameters where it found this one code. And this is how this program works. Now let's see this other things of this PCR file. We have discussed up to this line auto 0 or 1. Now this line represent lambda 1 and lambda 2 means it gives the information about this wavelength of your experiment. So right now we have the neutron diffraction data which was collected with the wavelength of 1.094 and we don't have lambda 2 contribution, but if you have lambda 2 contribution you can put this wavelength of the lambda 2 and then you have to also define this ratio of intensity between lambda 1 and lambda 2. Now other important thing in this is NCY. It tells that how much number of cycles this program has to run. Theta minimum is the theta starting of your measurement. This second thing is a step and this is the final theta maximum of your measurement. This I already told you that these are the background. And this guy is excluded region. So I have only one excluded region here, as you can see it from NEX equal to 1. Now let us see what are the other parameters. This 0. This 0 parameter is telling what is this overall shift in your pattern. So sometime if your instrument 0 is not exactly 0, means your 2 theta 0 is not exactly theoretically 2 theta 0, then this can have some value and this value can be refined. So this shift this whole pattern by some constant amount which is given by this refinement code. And the refinement code for the 0 comes here. So this code refines this 2 theta 0. Other important thing is here, this N8. It tells about number of atoms. So right now we have 5 number of atoms. You can see it 1, 2, 3, 4, 5. And other thing is this is the information about the space group. So there is some particular way on which this space group has to be written in the PCR file. And if you do not get sometime, if you get error, then you can write directly like the space group number. Let me try to run this to show you that this can run with this space group number also. So I put here number 212 and let me see if this program runs. This is my test data file and you can see it runs perfectly all right. So sometimes if you get error or you do not know how to write this space group symbol, then you can write the space group number directly here. Now we come to this most important part of this PCR file, which is the information about the structural parameter of your sample. So what you have here is 5 atoms and this first line is telling that first element is lithium and this X, Y, Z are the position and this B ISO I have kept it 0 but it has to be refined. And similarly now this occupancy. So this occupancy we discussed just now. So the lithium in this compound goes to 8C crystallographic position and the general position is 24. So the occupancy for the lithium becomes 8 divided by 24 which is 1 by 3. Nickel in this compound goes to the special site which is 4A, and as I told you, this general site is 24. Multiplicity of general site is 24. So if I divide 4 by 24, what I get is 1 by 6, which is the occupancy for this nickel, which is given by 0.1667. Now, similarly for the manganese, manganese goes to the site where the multiplicity is 12. So if I divide this 12 by 24, what I get the half. Similarly, oxygen 1, the site is 8C. So if I divide 8 by 24, I get 1 by 3, which is 0.333. O2 position is occupied by this oxygen, and this site is 24E. So the occupancy becomes 24 divided by 24 is 1. Now, can you get with this occupancy over formula? So like if I multiply this occupancy by some constant number, then I should reach this formula. So let's say if I multiply this by 3, then I get lithium 1, nickel 0.5, manganese 1.5, and this oxygen gives me 3 and this gives me 1. So by doing this multiplication of this occupancy, what I reach is the, so let's say here I have written the occupancy, and if I multiply everything by 3, so this becomes lithium 1. This guy becomes nickel 0.5. This guy makes manganese 1.5. These things make oxygen 1, and this makes 3. So total of this gives oxygen 4. So we have reached to this formula, which is lithium 1, nickel 0.5, manganese 1.5, and oxygen 4. So this is how we define this occupancy in this PCR file. And in principle, if you are doping some of the element at the position of this some of the element, then you can try to refine this occupancy and try to see how better you get the fit. These are these scale parameters. So it means it is your whole intensity is multiplied by this scale factor to match with this experimentally observed intensity. Now peak shape, as I told you last time, what peak shape we are using here is the pseudo void, and how we define the pseudo void peak shape is a, so this pseudo void function pseudo void, it is a weighted mean between a Gaussian and a Lorentzian function. So how I define this pseudo void is, so W is the weight and this is Lorentzian, plus 1 minus W of Gaussian. So there are other options in the full prof of this peak shape, as I can show you here. So suppose if I close this PCR file and go to the edit PCR and try to see what are the peak shape functions which are available to me. So let's see the peak shape. Right now we are using pseudo void, but you have many other options. You can see it. You have pseudo void with this axial divergence. You have split pseudo void. One can have triple pseudo void. One can. So there are a couple of peak shape functions which are available, and you can get this information about this peak shape function from the full Prof manual. And so other thing is that UVW. So this UVW parameters define the full width at half maximum for your sample, and this is given by, so your FWHM is given by U tan square theta plus V tan theta plus W. Here U, V, W are the function of collimation of your instrument, and sometime when you run this full prof, you get the error that your FWHM is negative, and this error comes because your UVW parameters in your file either in the starting are not correct, or while refinement they have gone in some wrong direction such that your FWHM has become negative. Other thing depends on your microstructural parameter, which I will describe later on, and this thing which is given by A, B, C, alpha, beta, gamma. So these are your lattice parameters, and this is like cubic system. So A equal to B equal to C, and these are the information about this preferred orientation in your sample. And these four parameters define this asymmetry of your peak at low angle. So these are the major part of this your full profile. So with this, now I close this full profile and let me try to run it and refine this couple of parameters. So I can run it from here. So I have make this test file as a data file. And let us say if you are running in the auto one mode, if I put any parameter, so these are the parameters which are getting refined. If I make it 0, I can refine this shape. And similarly, I think you can try to refine these parameters. And what you have to observe is that how is your calculated and observed pattern is looking. There's one more thing in this PCR is this. This last thing is telling you that what is the reason of this 2 theta, which you see when you do this refinement. So I can put it, let's say, around 5 to 60. So when this refinement runs, it will show me this 2 theta region. So let me try to do it. So you can see it. This is the region which the program is showing to me while the refinement. If I change this region, let's say if I put it, let's say around 30, oh, sorry, then it will show me the region between the 5 to 30. Now you can see that during the refinement, it is showing the region between 2 theta region between 5 to 30. So I think these are the major parameters which might be of interest to you. Well, let me tell you one more small thing. So this is the creep sheet. Let me see if it is here. Let's see, creep sheet. Okay. So this file I got from somewhere, and you can see this Meaning of this various parameter is written in this file. I'm not sure whether you can see it. Now I think you can see it, and I can scroll these parameters. So in case you want to note it down, this different meaning, then you can do it. So like, as I explained you that line 1 to 3, these are the information. Then job type tells you that what kind of job you are running. So if it is job type is 0, you are using this X-ray as a probe. If job type is 1, neutron as constant wavelength. If job type is -1, then you are dealing neutron time of flight data. If you put job type 2, then you are dealing with the pattern calculation for the case of X-rays. If it is 3, then you are dealing with the pattern calculation neutrons with the constant wavelength, like the reactor, as the case is ours. And if it is -3, we are trying to calculate the pattern for time of flight spectra. NPR tell you these profiles. So these are different profiles which are available in the full prof. NPH, as I told you, is number of phase. NBA tells you about this background. NEX is region to exclude during the refinement. NSC, I already mentioned that you might have user defined scattering factors. NOR, whether it is 0 or 1, it tells you that for the preferred orientation, whether you are using function type 1 or function type 2. And similarly, I think you can see this PCR file. I'm trying to scroll it very slow so that you can see the meaning of various code words which are there in this PCR, in this your PCR file. So like as I told you, auto 01. So code words treated automatically by the program. If I put auto 1 and if I put it auto 0, then it is manual mode, means you have to tell the program which parameters you want to refine. And I think similarly, so this is long list, and whether it is very difficult to keep all this parameter in your mind always, but more you work with this PCR files, more code word you can keep in your mind. So it is better to understand this PCR file from the text editor, because when you are running the PCR file and if there are errors, and if you understand the meaning of these errors of the parameter, then you can easily resolve these errors. I'm trying to scroll it still. So like experimental setup controls, lambda 1, lambda 2, I told you. And one can put this ratio also in the line number 8. BKPOS, origin of polynomial for background. This is cutoff peak profile tells in the FWHM units. Symmetry limit. So like theta minimum is tape, theta maximum. So I'm just trying to grow it slowly so that you can note it down or you can see it later on, that what are the meaning of these different parameters. So IRF tells you that method of reflection generation. STR parameters tells you that size distance broadening, how it can come. And this ATZ parameter is useful for this when you want to analyze this phase fraction. If you have more than one phase in your sample and you want to find it out, what is the phase fraction of one phase and another phase. This NVK, which is number of propagation vector, it is helpful, and we will see it when we want to refine this magnetic structure. B iso tells you about this Debye-Waller factor, means isotropic B factor. It can be anisotropic also. There's an option in this program to keep it anisotropic. The scale factor, profile shape parameter, UVW are the half width parameters. This X and Y, which you see in this PCR file, they tell you about this Lorentzian isotropic strain parameter or Lorentzian isotropic size parameter. Similarly, you can see in the same line, you have this UVW, X, Y, Z, Gaussian, Lorentz, and size model. These are the models which you can decide depending on your system on which you are working. So there are other things which you can go through it. So this list is long. So this is the end of this file now. So I think if you try to keep some of these parameters in your mind, it will be of help to you when you are running this PCR file. Now we have finished this refinement of this crystal structure. Now this full prof allow you to see this crystal structure part. So how you see it, you go in this run full prof studio, file, open, and once you finish this refinement, it generates a studio file which is called full prof studio file. Let me see if I can locate this file here. So you can see this is the information about this. You can zoom it. So this is the information about your crystal structure. Here a couple of options exist like box limits. So you can define the size of your unit cell, like I can make it between 0 to 1. So this is how my unit cell looks like. So if you want to see the input of this file, so these are the input of this file which has come it after you run this full prof program. So it means by using this full prof studio, you can visualize how your crystal structure looks, where in your unit cell various atoms are going. There is an option to multiply this unit cell. You can hide some of the atoms. You can display them. You can display H atoms, hide H atoms. There are a lot of options here, which I think you should try to play with this program. So these are the information about this structural parameter. Now, but our main interest was to understand the magnetic structure. So now, how we understand the magnetic structure? So let me show you the data. So these are the data at, let us say 50K by sigma 105K and let us say, I think Curie temperature for this material from this DC magnetization study is something like 120K, correct. So let's try to see this file around 140K. So as you can see it, 140K below we have the magnetic intensity. Now best is to go at low temperature and then try to understand the magnetic structure, or you can see this temperature evaluation of the magnetic structure also. So here we have the additional peak, and the idea is to now determine the magnetic structure of this compound. Let me quickly remind you that how we define this magnetic structure in the full prof notation, and what are the steps now which are involved to determine the magnetic structure. So how we define this magnetic structure is, let's suppose this is your unit cell. Sorry. Is it? Suppose this is my unit cell, I'm putting it into dimension, and suppose I have a magnetic atom which is sitting at this location here, and it is carrying some moment. It is carrying some moment. Now, how we define magnetic moment of this atom, let us say J, in the unit cell having as the origin of the lattice as RL. So suppose this is the atom, and how I define, and suppose this is the RL, so means this is my lattice cell and this atom is sitting at the location RJ. So it means RLJ, which is the position of this atom, I can define it as RL plus RJ, where RL is nothing but it is pure lattice translation. So these are the translation of your lattice. Now how we define the magnetic moment of the atom which is numbered J, I define it as M of J is equal to sum over K. K is here called the propagation vector of magnetic ordering. So how I define it is Sk of J exponential 2 pi iota K dot RL. Remember this, in this exponential, what I am taking it as R of L. And this Skj, they are called, so this Skj is called Fourier coefficient. So this Skj here, they are called Fourier coefficient. And they are complex vectors. As the moment has to be real, so Sk of J is equal to S of star minus K J. So to define this magnetic structure, what we need to know is about this Fourier coefficients. And this Skj, this Fourier coefficient, so this Skj, which are called Fourier coefficient, they have the same unit as magnetic moment. Now here in some of this literature or some of these books, you find this factor in this exponential, which I wrote it as 2 pi iota k dot r l they write it as, instead of RL, what they write it as RL of J. It means they include this both factor, means position of this atom and the pure lattice translation. But remember, when they write like this, then the Fourier component or the Fourier coefficient in that case is related to our Fourier coefficient. So our Fourier coefficient is this. It is related to the Fourier coefficient in this case, which is TKJ by a phase factor 2 pi iota k rj. So they are related. So means at the end the things are the same. So don't confuse about this. Now when I am writing this exponential factor 2 pi iota k dot RL. So this RL for the primitive cell is given by, let me write this RL for the primitive cell. So RL in our case for the primitive cell, it is given by N1A plus N2B plus N3C. But if you have the, which is called RL is equal to Rn, but if you have the centered cell, like if you are not working with the primitive cell, you have a centered cell like body centered, face centered. In those cases, you have to take into the account this translation vector also. So in those cases, you have to take these vectors also into the account. So here this is called centering vector. So if you are not dealing with the primitive cell, then you have to take this centering vector also into the account. Now this Skj are the Fourier coefficient, and let's say assume if your propagation vector is, suppose you are dealing with the case where k is equal to 0, 0, 0. So in these cases, your MLJ is equal to Fourier coefficient. So your Fourier coefficient is directly your moment, and magnitude of moment in all cell is identical. But remember, what we are dealing it here is the conventional cell, and K and H are with respect to the, please remember this, with respect to reciprocal basis of conventional unit cell. And when you have this propagation vector, and if you see this neutron diffraction pattern, you will find the magnetic break peak at the location which is given by H plus T. This is how you define this propagation vector. So if you have this propagation vector K, you will find this magnetic break peak. So if the H is the nuclear reciprocal lattice vector, so H plus K position, you will find this magnetic break peak. So suppose if you have K equal to 0, then the position of this magnetic break peak is same as your nuclear break peaks. Now please remember, the K equal to 0, 0, 0 do not mean that we are dealing only with the ferromagnetism. You can have K equal to 0, 0, 0, and So K equal to 0, 0, 0 can give you ferromagnetic, antiferromagnetic or ferrimagnetic kind of ordering. Like K equal to 0, 0, 0 telling a ferromagnetic kind of state is true if you are dealing with a Breve lattice with a single atom per primitive cell. But what we are dealing is we are dealing with this conventional cell. And example of this that you have this kind of ordering with the K equal to 0, you can see in the literature this LAMNO3 lanthanum magnet, which is antiferromagnetic structure, and this propagation vector of this magnetic ordering is 0, 0, 0. Another example which we solved in our lab couple of years ago is NDFeMnO3. Here also K equal to 0, 0, 0. However, the magnetic ordering is antiferromagnetic type. Please be clear about this point. Now, case number 2 can be your K. Suppose if your K is half of H, means K and minus K are equal, then also your Fourier coefficients are directly moment. But if your case that K is not equal to minus K, then in this Fourier summation, you have to take the summation of wave vector K and minus K both. Now, how we describe this symmetry of this magnetic structure? There are two ways to describe this symmetry of this magnetic structure. First is via using Shubin-Kov group, and second is the formalism using propagation vector, which we plan to do it. So this second is more general formalism. So this Shubin-Kov groups, they are defined only for the commensurate magnetic structure. And what I mean by the commensurate magnetic structure is, let's try to understand in the simple language. Suppose you have that magnetic ordering and the magnetic cell is, let's say, given by AM, BM and CM. And if I find out how much it is related with the nuclear cell, let me divide this by, so these are the nuclear cell. And suppose this is parameter P, Q, R. If this P, Q are rational number, then we call this as a commensurate ordering. So in this case, your magnetic unit cell is, let's say, 2 times in some direction or 2 times in A and B direction or 3 times. So this your magnetic unit cell is rational with respect to your nuclear unit cell. But if you have this integer which is P, Q and R, or one of them, if they are irrational number, then what you deal is the incommensurate magnetic structure. And now how we deal with the determination of magnetic structure in this part? Let me write down the recipe. So first part is, as I told you, determine propagation vector K. This is the first part, and this part you can do it by carrying out neutron diffraction experiment below and above the magnetic ordering temperature. Then second part is find out this little group of K, which is called GK, and its irreducible representation. So I think at this stage, I'm not sure how much of you are aware about this uh, group theory and how to get this irreducible representation. There are a couple of ways to get it. There are some software which exists, or you can do it by paper and pen. So maybe I will just describe you about this software which are available to do this irreducible representation. And main hypothesis of this magnetic structure determination by this method is that this Landau theory of second order phase transition which says that at the phase transition, means after the phase transition, only one of the irreducible representation survives. So our idea is to find out the irreducible representation. So this Fourier component of this moment, Skj, they can be written as summation of this basis vector and our idea is to determine by this approach this basis vector for the magnetic ordering. This basis vector, they are vectors and they determine if your second order phase transition, what kind of direction your moment can take. And once you determine this basis vector, then these are the coefficient and these coefficients are refinable. So by refining this coefficient, you can determine the magnetic structure. Now let us go to the step one, that how we determine this propagation vector in experiment. So let me try to plot this low temperature data. This is XY sigma format. And let me try to plot this data which is in the paramagnetic phase. So 160K is the paramagnetic phase. Now the idea is we can take the difference. So we just try to focus the region which is at low Q, because our magnetic peaks are expected at low value of Q only. So now we see there are 4 peaks. Now we can go in the calculation and now we have to find out the position of these peaks. It is always better to work with this refined file, and if these positions are same, so I know I have to take this account, this 4 peak position. So I file reset, I go in the PRF file of the pattern which we refine. Now I know I have the magnetic intensity at these 4 peaks. Enable peak, I think disable. I have to see peak selection, enable, and then what I have to do is insert peak. So I would like to insert manually, and this position has to be very carefully noted down, because with this position only it is going to tell us about the K vector. Calculation, save peaks, K search format. So the K search is the program here which will search in the reciprocal space about the position of this peak and will try to tell you what are the probable propagation vector of your magnetic ordering. So this information it has taken from this PCR file, and if you click it, so it gives this K equal to 0, 0, 0 as a first preference, and now we will start from this K equal to 0, 0 propagation vector, how we determine this basis vector of this magnetic ordering. So how we do it? Then we know this propagation vector, and let's go to this program. And then for determining this irreducible representation, there is a code which is here written as a base irreps. So this needs some input. So let's write some code. Code you can write something like magnetic structure. Working directory you can define. I was working desktop. Okay. Then title, let's put it magnetic structure. And now you have to tell it the space group. So space group which we were dealing is was P, capital P, 4, 3. This is how it is written in this. And the K vector 0, 0, 0. You can see this Brillouin zone level. It is gamma point, so you can say G. Now you have to define the moment which is axial vector. And let's start with this one moment, one site, which is, let's see what was the location of that site. So let me start with this nickel 0.625625. Now I say this is atoms in the unit cell. You can go with the explicit sublattice, but then I have to write all 4 nickel here. Either you can select short output or long output, and then you ask it to run. And now it generates 2 files. One is this BSR file, and another is this full Prof FP file. This FP file directly you can use in the full Prof refinement. But briefly, before I close for the day, I will tell you. So these vectors which you are seeing it, so they are the basis vectors, set of 3. And now this basis vectors will determine what is your moment direction. In the next lecture, then we will try to determine the magnetic structure of this compound using this basis vector. Thank you. If you have any doubt, you can text.
I will make some like wait, ask you. I'll just say. Hello, I'm Saibal Basu. Dr. Anil Jain has been teaching you about these techniques. I know some of you might have done group theory, some of you might not have. So, basis vector and irreducible representation might be something which you have not been introduced earlier, but I will request you that please follow the process of fitting. If you are in physics, you cannot avoid doing group theory, whether you are in condensed matter or particle physics. So a little bit of group theory possibly will introduce you just enough for you to understand. Like you can see here, he has been talking about basis vector. What are basis vectors? In the simplest form, you know, you have a 3-dimensional real space. I can put x, y, z. Then I have I, j, k as basis vectors. Direction, cosines will be deciding. And the length in each basis vector tells you a point. It's something very, very similar to that. Or you can choose r, theta, phi coordinates and define a point in spherical polar coordinates. So here the basis vectors and irreducible representation comes from the symmetry of the whole magnetic system. So this will give you a brief introduction to it, enough for you to understand the process of fitting, which is of base interest to us. And later you have to learn group theory with this introduction. Thank you. And the next lecture will be on Friday. And now you can ask Dr. Jain any questions you want to. Any questions, Amra? नहीं है तो